Physical science classes, we are now hopefully kind of learning a little bit about motion. You should have the last few days explored how we can explore motion with oil drop diagrams or dot diagrams. This is going to be a quick lesson on position versus time graph. So we can have diagrams, we can graph it, and then tomorrow we'll do calculations. So this is going to be kind of quick and less than we do in class, but it should be enough to get you through. When we look at the way that we graph motion or how things move, it's very important we understand the axes we're looking at. So what we're going to be graphing is the position, which sounds weird, but position is just how far away are you from your origin. Your origin is, it's a set point that we're going to call our zero, if you will. We're also going to look at how it changes over time, and we know that both of these things are important when we're talking about motion. If I run 1 mile in 5 minutes, versus if I run 1 mile in 10 minutes, the time makes a huge difference in how fast that motion is. So it's very important when we show this with a straight line on these graphs, and they won't always be straight. We'll talk about what that means in a minute here. But we need to think about what the slope is trying to tell us. And you know from all your other math classes that slope is always rise over run. And what that means is how much our y-axis is changing in terms of our x-axis. And in this case, we can go to C. This is meaning how much is our position changing in a certain amount of time. This is very important for us to think about. So if we look at this graph, for instance, this person started 1 meter away from the origin, and they ended up 6 meters away from the origin. So that means that they walked or went 5 meters, and if we go look down here, that took them 5 seconds. So if we take rise over run, or their position over their time, they went 5 meters in 5 seconds. The slope of a position time graph will give us the speed of that object because it shows us how far they went and how long it took them, which is what speed truly is. It's important you understand on this graph, every single second they went 1 meter, which is what we call constant motion. That's why it's a straight line. Every single second they went the exact same distance they did as before, which we call constant motion. So looking at some different things we need to understand here, this is a graph with 3 different types of motion. There's a biker, there's a runner, and there's a walker. And what we need to understand here is that all of these things are moving away from the origin. But if you look, the biker, for instance, went 25 meters in less than 2 seconds. He's going fast. The runner also went 25 meters, but it took him more like 5 seconds. So he went just as far as the biker did, but not as fast. And lastly, the walker only went 10 meters in like 6 seconds, so he's not going very fast. So what we have to understand here is that how steep these lines are tell us how much distance or position are they covering in a certain amount of time, and that the steeper the line is, that means they're going that distance in less time, and if you go the same distance in less time, that means you're moving faster. So a very, very steep line would mean something's moving very fast, whereas the closer it gets to being flat, that means they're not covering very much distance in a long time, which means they're moving slower away from the origin. We need to make sure we also understand not every graph is going to be just a nice smooth straight line. So different slopes represent different motions. If we look at this one, it kind of, a lot of kids think, well, maybe they're starting up and then they're climbing a mountain. That's not it at all, guys. What we're looking at is how its position changes just from a starting point and how we compare that. So if we go give these different signs, if you will, let's call this starting part A, this part B, this part C, and this part D. And if we go to explore these different parts of motion, what we have to understand here, maybe this is my classroom or my mailbox. It just means I'm not going to start exactly at my mailbox. I'm going to start 20 meters away. If you look after the first second, then it looks to me like A is still 20 meters away, which means at this point, if it's a flat line, its position isn't changing and it's just standing still. When we get to part B, though, we can see that our slope changes, which tells us something. It now starts to walk away from the mailbox, away from the mailbox, away from the mailbox until it gets to 3 seconds. So for B, it's not that it's climbing upwards, guys. It's just moving away from our starting point or away from our origin. When we get to C, we are 60 meters away from our origin, 40 meters away from where we started, and then I'm still at 60 meters, I'm still at 60 meters. What does that mean is happening at part C? That means I'm standing still again. So, we now though, right here, it doesn't mean that I start to tunnel underground. What it means is that I turn around and I start to walk back to my starting point and start to walk back my origin. It doesn't mean I'm moonwalking or I'm going underground like a mole. What it means is I'm just walking back towards my starting point, and that's kind of what we show here. Part A is just standing still. Part B shows they're moving away at a constant speed. We know that because it's a nice straight line. Part C, they're standing still, but they're just further away from the mailbox. And Part D, they turn around and move with a constant motion back towards the mailbox. If we were to see one like this, I doubt you will in our class, but this does not mean somebody's doing a loop-de-loop in time or anything. It just means right here at the start they're going fast. Here it's less steep, so they're not going as fast. And as it gets to be flat, that means that they're standing still. So this is an example of something slowing to a stop. Because it's far away, it's going steep, it's less steep, it's less steep, and here it flattens out, showing that their position doesn't change. This would be an example graph of like a car coming up to a stop sign. This is our last example we'll do here, and this will help you guys on your little assignment and your little quiz. So this looks like a very complicated graph, and make sure, if we see here, we're starting at 0, we're not going up and then below the ground. We're just changing our position over time to look at that motion. So here's like what we probably end up doing for a bell ringer in class. So it says, which portion of the graph shows the object moving towards the origin? So if we look here, like part A, it's moving away from the origin, because here's where I'm starting at 0. Part B, it's not coming towards it at all. Part C turns around and is coming back toward the origin, but I have to be really, really careful here. Because part D, I'm now at the origin, but I keep walking past it, which would mean here I'm moving away from the origin. But then I turn around at part E here, and what am I doing? I'm walking back towards my starting point and my origin. So if we look here, the first part, the only parts of this graph moving towards the origin are part C and part E. Moving on now, it says, in which portion of the graph is the object moving at a steady pace? Steady just means it's staying nice and even and it's not changing. So actually, A is moving, C is moving, D is moving, and at part E, they're all moving at a steady pace because the lines are straight. The only part of the graph it's not moving is part B, because it starts at 60 meters away and it ends at 60 meters away. And what that means is it didn't move at all. So the second one would be every part of the graph except portion B. Now that just leads us into number 3. In which portion of the graph is the object not moving? The only time that its position isn't changing is part B. That flat curve means it's staying the same. Number 4 says, which portion of the graph shows the object moving away from the origin? So this is the exact opposite of what we talked about earlier. On part A, they are walking away from our starting point. On part D, here they've reached our origin and then they keep walking past it, meaning that they're moving away from the origin until they turn around back here. So that would be part A and part D. Number 5, we might need some math, but if it says which portion of the graph is the object moving the fastest, that would mean it's the steepest because it's covering the most position per time. And if we wanted to do the math, we could, but if we go look at part A, in 5 seconds, it's by far and away covering the most ground than C, D, or E, which means A is the fastest because it's the steepest. Number 6 is one a lot of kids miss. We'd need some work. It says, what was the speed of the object on part A? Well, if I go look at part A, it started at 0. It went up to 60 meters, which means his distance he covered was 60 meters. If you look at the time it took for him to do that, it took 10 seconds. So our slope, if he went 60 meters in 10 seconds, that would mean his speed is 6 meters per second. And it's that way the whole way through, since it shows us that nice straight line. Number 7 says, at what time was the object farthest away from the origin? If we look here at B, it's 60 meters away. Down here, when we turn to part E, it's 40 meters away. It doesn't mean it's underground, it's just 40 meters the other direction. So the farthest away from the origin is part B when it was 60 meters away from the graph. This should help you guys getting started with your assignments. Just take your time and think about what the graph is trying to show you and think about the position and how it's changing versus the origin. Good luck.